Okay, we're going to be starting our discussion of descriptive statistics. Now, descriptive statistics are things that you have used ever since high school. So that's things like means, standard deviations, things like that. What you basically are doing is having one variable or a number of variables that you're describing the nature of that variable itself. Well, in this class, we're going to be writing a long paper. And the assignments that you're going to be using throughout the course are going to build up that paper so it gets longer and longer per assignment. When you're done with your magnum opus, when you're done with your big paper, you're going to have to take that paper and ask yourself, is the question that you're trying to answer in that paper, is it understandable? Do you have an idea of what it is you're trying to look at? That fundamental question is the hook. Like when you're reading a novel, you have to have a hook, something that grabs your attention and brings you into that novel. That happens in the first 1/4 to 1/3 of the paper. So, in that beginning section of your magnum opus, you have to use descriptive statistics. You have to show people what it is that you're trying to describe. You have to show people why the question that you're asking is relevant. You don't jump right into the multiple regression analysis, the fancy statistics, the use of three-dimensional graphs. That happens in the second 2/3 of the paper. The first third of the paper has to motivate your reader, or that reader will not get to the second 2/3 of the paper. So you must have descriptive statistics. So what we're going to do today is focus on how to use those descriptive statistics in R. How to get them, how to get some basic plots, how to see things on the computer that are useful to us. Okay, so what I'd like everyone to do is go to my website, courtneybrown.com. Is there anyone new to the class today? Okay, so go to my website, courtneybrown.com. After you get to my website at courtneybrown.com, click on the third link for the student area in Emory, and then click on Assignments. And you want to see Assignment 1. So does everybody have this page in front of them? Okay. What we're going to be doing today is analyzing the on-year, off-year pattern of congressional mobilization. With this pattern of congressional mobilization, we're going to be able to look at means and have descriptive statistics that show that something has happened in the congressional mobilization that we would want to understand. So, we are not going to be doing a formal test to see if, in fact, those descriptive statistics are really saying the story that we want to do. That's going to happen in the second assignment. Today, we're just going to look at the means themselves and see if they look different, sort of ballparking it. Now, with statistics, a number is never a number. There's an old joke. A little kid, 9 years old, goes up to his daddy, who's a university professor, and says, "Daddy, my math class just told me that I have to be able to determine what numbers are when they're adding. So I picked a simple one, 2 plus 2. Why don't you tell me so I can tell them what 2 plus 2 is all about?" And the dad said, "You know, this is the great opportunity for me to show you about the resources at the university." So the resources at the university are like this. If you go to different departments and to speak to different faculty members, they will have an immense wealth of knowledge, and you will then be able to understand that there is so much that you can learn by having these resources around you. So we're going to go to the university, my place of employment, and we're going to ask them, faculty members, the actual question that you have so that you can see how rich the knowledge is that you're going to be marching into as you get older. So the dad took the kid the next day, went to the math department, and found his good friend in the math department and said, "My son has a homework assignment. He's supposed to determine what 2 plus 2 is and to be able to defend it." And the professor at math looked at him, smiled, looked back at the dad and smiled and said, "Young master, you have come to the right place, because that's what we study, numbers. We know exactly what 2 plus 2 is. 2 plus 2 is exactly 4. The dad was beaming. Everything so neat and tidy, couldn't get better. So he said, "But young son, you have to see that there are other places you could go. You don't have to go to one place. I don't want you to think that there's just one spot where you can go and there's no other places. There's knowledge everywhere you look. So let's go over to, hey, people who work with computers, they do things like that. Let's go over to the engineering department." So we took him over to the engineering department, and he found a good friend of his, a professor in engineering, said, "Now look, I know what you do. You do things differently than they do in the math department. My son has a math problem he has to defend in class, and he wants to simply know and be able to defend it. What is 2 plus 2? And we thought you'd be able to give him some insight so that he could then answer for his homework assignment." And the engineer beamed at him, and he beamed at the dad and said, "Young master, I can tell you just what that is." You see, we use computers to hone in on answers no matter what we do. We always use computers. We just use, and what we do is we get these computers with complicated programs, and they find the answer in a general realm of phase space. And then when they find the answer in phase space, they asymptotically approach it as they get closer and closer to it, like a spaceship flying through the heavens, getting closer and closer to a planet. So 2 plus 2 is within a boundary somewhere between 9.1 and 4.1, depending on the level of the accuracy in the algorithm you're using. The father sort of looked like he was happy. Oh, okay. The son looked totally confused. And then the father said, "I know what we'll do. We'll go." We went to 2 different resources. What we have here is a perfect opportunity to learn. So what we're going to do here is say, let's go to a 3rd authority at the university, because if you have, life is complicated. You're not just going to get one simple answer for everything. You're going to have problems you're going to have to resolve. This is perfect. So let's go over to, my friend in the statistics department. That'll be perfect. He'll help us resolve this. And so he took his son over to the statistics department, found his good friend in the statistics department, and said, "My son has a homework assignment, what 2 plus 2 is, and he has to defend it in class." And you see, we went to the math department, and we talked to so-and-so at the math department, my good friend, and he said it was exactly 4. But then I talked to my other friend in the engineering department, and he said it was within a boundary of one number, a lower bound, and an upper bound, converging onto an approximate number within the realm, sort of in the neighborhood of something. But so we thought we'd come to a 3rd authority and sort of help resolve this, what 2 plus 2 is, so that my son can understand the richness of the knowledge at the university. And the statistician beamed, and he looked at the father and he beamed, and he looked at the young little kid and he said, "Young master, I can tell you precisely what it is. 2 plus 2 is," and he leaned over to the little kid and said, "What do you want it to be?" That's the answer. The answer is, there is no such thing as a solid number. It's what do you want it to be? That's the answer. I have seen situations which people say, this is a number, and this is the correct number. And I looked at them and I said, they're nuts. You can't say that's a number. A number is never a number unless you test it. And then it's only a number within a bounds. For example, I have actually seen situations, I won't give any names or anything, but I have actually seen situations where people were accusing somebody of having a high number of A's in their classes, giving too many A's, calculating the A's, the number of A's that they were giving. And I looked at the way they were doing it and I said, that's crazy. You're looking at the average for that person and then the average for, say, a department. But the averages are being calculated without respect to how many students there are in the class. So if the person has an independent study with 1 student and gets the A, that's being counted the same as 3 A's in a 45 student body, in a 45 student class elsewhere. You go 100% plus, say, 0, or even just 1%, add that together, divide by 2, you get 50%, right? I mean, it's crazy. The reality is the person only gave, say, 4 A's, and you're saying he gave 50% of the A's of the class of the course up an A. I said, and then you're saying, well, also you're saying that this number that you're saying for that professor is greater than, say, a department average, because you're saying this is the number and this is the number for the department average. You can't do that. You literally can't say a point something or other is bigger than another point something or other, ever. You have to actually do a test. You have to actually say this number has a bounds around it, because the person doesn't give exactly that number of A's in every class. There's a deviation. There's a realm around which it's different. And then the department, every faculty member doesn't give exactly that number of A's. There's a realm around that average. Well, those realms around those averages overlap to the point where you can't tell if a number is different from another number unless you give it a test. So with statistics, actually with almost everything dealing with reality, every time you hear anybody say, this number is different from that number, you should, after having taken this course, say, prove it. Be from the state of Missouri, the show me state. If you're saying this number is different from that number, prove it. Prove it. I want to see it. And you say, what do you mean? Just look at it. That number is bigger than that number. Each number has a test. So that's what we're getting to with assignment 2. The test, to see whether numbers are different from each other in reality. What we're getting to in assignment 1 is just the numbers themselves, but we're not using a test. So you should understand you're just ballparking it now, the way so many people do it. The test comes next week. Why is it so important to do the ballparking now? Because it introduces you to the R programming language. You get to see how these averages are calculated. You get to see the general nature of the problem. And you get to see how you can program things to come up with your own answer. And also you get to use plots and get some plots that are very useful with R. So let's do this. First of all, let's read the assignment. In this assignment, you will analyze the on-year, off-year pattern of political participation in voting during the U.S. congressional elections. Now, it works like this. Every 4 years, there is a presidential election. People are really excited about the presidential election. There's a lot of advertising that's going out for the presidential election. There's a tremendous amount of excitement that brings people to the polls. And while they're there, they say, well, I might as well keep on voting. So they vote for governor and congressman and senator and dog catcher and everybody else. Okay? But what about 2 years later, when there's only a congressional election and there's no presidential election? A majority of the people, like a vast majority of the people, a huge number of people just say, I'll just forget about this one and I'll stay home and watch TV and who cares? And they wait for the next presidential election. So what happens is the number of people that turn out for the congressional elections is much bigger during a presidential election year and much lower. So what you get is a sawtooth pattern. Now you need to actually look at the right measure to see this. What you see in the mainstream media when you're looking at the election results is not an issue, is not a number that can be used to measure how many people are coming out. It's a number that tells you how many people voted for a certain candidate. What that's talking about is a vote share measure. Now a vote share measure is not what we're going to use today, but that is the vote for party I, Democrat or Republican, divided by the total vote. So that's the proportion of the vote for a party. We're not interested in that. Okay? What we're interested in is vote mobilization. Vote mobilization is something different. What we want to know is, what is the total number of people that voted? Okay? Divided by not the total vote, because we already know the total number of people that voted. We want to know the total number of people that voted divided by how many could have voted, the total eligibles. So here we have, in the case of the United States, it would be the Democrats plus the Republicans. So here we have total vote, total congressional vote, divided by total eligibles. And that would give us the proportion of the vote that would give us the proportion of the electorate that actually voted. So let's look at this. This on-year, off-year pattern of political participation is going to produce something that looks like this. Let's say we have 1950 here, 1952, 1954, 56, 58, 60, 62, and so on. 1950 was an off-year election. That's where the congressional vote happened without a presidential election. 1952 was a presidential election as well. So you're going to get a sawtooth pattern that looks like this, where all of these elections at the bottom of the teeth are off-year elections, and all of these elections at the top of the teeth are on elections, where the election took place on a presidential year. Okay? So we're looking at political participation and voting during the U.S. congressional elections. In on-year elections every 4 years, the congressional elections coincide with presidential elections. More people go out to vote in those elections. In the off-year elections, the elections between the on-year elections, fewer people vote. Thus, congressional electoral mobilization is a proportion of the total eligible voters is greater in on-year elections than in off-year elections due to the structure of the electoral calendar. You have, and on the vertical axis here, you have congressional mobilization. So congressional mobilization is higher on the on-years. You need to do this assignment in two parts. First, you need to obtain the data that are used for the assignment. The data set is called usparty.txt, and you can get it here. And we're going to click on that. Now, this assignment is done down below, both in R and in SAS. So we're going to do the R version of it. So the SAS code that can be used for seeing how the actual data set was created is actually available here if you're interested in that type of trivia. It's actually pretty easy to read what was actually going on when I made it. So what you're going to be doing now is taking the data set and putting it in a directory or folder called your R working directory. Now, we're going to conduct the analysis for the years 1950 to 1988. Now, here's a partial code book, meaning what the actual variables are. We're going to be dealing with two variables, essentially. But what we want to do first is create, in your hard drive, on your computer, an R working directory. Now, this working directory or folder, let's call it actually that, R_working_directory. Now, you have to create it in some place that you want to have it. And everything that you use in this course using R, you're going to dump in that directory. All the data sets you're going to dump in that directory, your R programs you're going to dump in that directory, and it's going to be really simple because as long as it's in that directory, R is going to know where to look for it. And you won't have to specify with R some fancy location on your hard drive where it is. If it's there, it knows it. So we have to first tell R where your R working directory is. So first of all, everyone on your computer now, where do you want it? Find a nice spot that you'll be able to find it again later and create a folder or directory called R working directory. Let me show you what I do on my computer. All right, so here's my computer, and I have two disk drives. I have a C drive and a D drive, and you see I have something here called the R working directory. Okay, and I have a couple zip files in there as well. See that R working directory? It didn't matter where I put it. I could have put it on my C drive, but I tend to put everything that I use in classes in my D drive. It's the same disk, I just have it partitioned to two different drives. You don't have to worry about that. Just find some spot on your hard drive where you want to call it, and call it the R working directory, and just make it right now. Do that right now. Now the next step is to tell R that that's where it is. We have to tell R where it actually is. Okay, anybody not do that yet? Okay, now let's tell R where it is. Now there's different things for different things. Let's start with the Windows people first, okay? With the Windows people, I'm going to right mouse click on the R icon. Everyone see my R icon on my desktop? I right mouse clicked it, okay, and I look at properties. Now, take a look at this properties. So, you see this start in, and then I have my drive number, / and then the R working directory. I actually put it there, in the start there. So if you're using a Windows machine, type the actual directory location right there, wherever you actually put your R working directory. Okay? Now if you don't know your directory location, you can find that with Windows Explorer. And if you click on Windows Explorer, you can click the top bar of Windows Explorer and it will convert it to the actual thing, and you can cut and paste that. Okay, so you just find your R working directory, click someplace in that top bar, and you'll get your R working directory, and you just cut and paste that into it. Okay? Now, the Mac people, you can do this with... There's another way to do it. Let's actually... And sometimes, especially the Mac people, sometimes like to do this as well. Change, it's under miscellaneous, change working directory.
Okay, thank you.
Does everyone see? Again, I myself get sort of, the Mac people do change working under miscellaneous. Does everyone see where it says miscellaneous? Okay. Okay, are you okay? Okay, so you have to put the directory address there. Okay? Okay, now, once that's done, get out of R and start it back up and see if it works. Now, actually, before we actually get into R, let's actually put the data set into that directory. So what we want to do is go here and click on the data set, which is here, the zip file, okay? So you want to actually click on that. Okay, and you want to save it. Now this actual file that you're clicking on here, you're going to actually take that, and that's actually going to have all the data sets for the whole course. You're going to dump that into the R working directory. Do that now. Dump that into the R working directory. And now you have to unzip it. Everyone know how to do that? Everyone should be okay with doing that. If you're a Windows machine, right mouse click and say extract. The Windows people just click on it and it should be self-explanatory. Okay, who has not done that? Okay, now the trouble is you're going to have a folder inside your R working directory that has this zip file, that has these data sets. In my machine, let me demonstrate what it will look like. The point is, you want all of the files that are in your directory not to be in another directory inside the R working directory. You want to be at the top level, so you want to drag them to the top. What we're going to be doing here is using this variable here, mtotcong. Mtotcong is the mobilized total congressional vote. It's the proportion, and this was gotten by taking the total congressional vote and dividing it by the total eligibles. Total eligibles. All right, so, and the eligibles is another variable here, which is just the eligible people that were able to vote. Okay, so let's now go back to the instructions, which we go down here, you are to look at measures of central tendency. In this case, we're dealing with arithmetic means. And variation for on-year, off-year congressional mobilization between the years 1950 and 1970. And compare these numbers for the same variables between 1972 and 1988. So you're going to look at this sawtooth pattern from 1950 to 1970, and you're going to look at the sawtooth pattern again between 1972 and 1988. You're going to be using R programming language to do the assignment. Now, I did use SAS in earlier years, so the SAS code for doing this whole assignment is down below. Those of you who like looking through things like that are feel free to just sort of scan it. SAS is pretty easy to understand just by looking at it. But immediately below is an R script that will get you started, and you should study closely this script as you begin to learn R. You will need to finish the program to get the on-year, off-year patterns means for 1972 and 1988, meaning I do it for you for 1950 to 1970. You have to do it for 1972 to 1988. It's basically cutting and pasting the appropriate lines and changing the years. No big deal, but it gets you to play with the code to start off. Okay? Now, we're actually going to go through this line by line. So let's actually do something before we actually go through it. Let's actually see it run. So what I'm going to do is take this code and I'll put it into RStudio once so you can sort of see me do it. But then I'm not going to use RStudio that much, even though you're going to be using it. I'm going to use something really crude like WordPad or something like that, because I don't want you addicted to RStudio. I really want you to see how R works, what I call raw R, so you can just use any old. I often use Dreamweaver for my text editor to do my R code, because I end up putting everything up on the web anyway. So RStudio is nice, but there are many other editors that you may end up liking to do. A lot of people like RStudio, but there's also TinR, there's other kinds of, there's all types, and they compete, and they're all free. So these people are competing for your attention, and you're not doing anything except looking at them. You're not paying them any money. So as the years go on, you may want to switch your editor and things like that. So I'm going to be using something really crude, like a crude word processor, but I want you to be able to just sort of see how RStudio works. So what I'm going to do now is take this code and just input it I'm going to copy it. Okay? Now, the first thing I'm going to do is input it into R, and then I'll input it into RStudio. Okay? So if I input this into R, I go right mouse click in the console. This is just raw R. Okay? This is just R running by itself without RStudio, without anything. So I'm just going to right mouse click it and paste it in there. Normally you would not do this. If you were writing your own program, you wouldn't post it just here. You'd first post it in a word processor or an RStudio or some other text editor so that you can actually change it. The only problem with using a word processor is word processors correct the spelling, and computer code has all types of spelling. You don't want it to do that. It puts punctuation in there. It does all types of crazy stuff. It has formatting commands. So if you do use a word processor for something like this, you have to use a really primitive word processor, something like WordPad, something that doesn't do anything to it. Okay? All right, now, so I'm going to just paste it in there so you can see what actually happens. All right, does everybody see? The R code went into the console. This is the place where the program goes. And then the output came out here. Notice it has graphics devices 4. That means there's 4 different plots. This is what we're going to do. These plots are print ready. These are to die for. They are really good. Razor sharp, like they're done with Indian ink. Prints on a laser printer really perfectly. Now, notice how I have different windows for all of these things. Okay? This is not what it looks like for the Mac. So all of you people, do exactly what I just did. Cut and paste that program and just paste it in. You may have a problem with the Mac it may or may not work with the Macs. Let me tell you why. Sometimes with the Macs are a graphical-oriented machine to begin with, ever since the original first Macs. That's how Steve Jobs thought. So what it does is it takes a lot of the formatting commands that are in the web page that you don't actually see, and it remembers them and it puts them into the console, and sometimes it screws things up. Okay? So RStudio clears all that stuff out. That's also the same problem with posting it into a word processor. Sometimes the word processor remembers that. Windows machines, originally Windows was a text line editor command driven thing. It was not a graphically oriented machine to begin with. So based on the history of the development of Windows, it gets rid of a lot of those formatting commands anyway. So you don't have the same problems like that with the Windows machines that you do with the Mac, because so for the Mac you often have to be very careful to make sure that those other commands that you don't see don't also get posted into it. Okay? RStudio will take care of that for you, or you can do things like post it. You can try using something like TextEdit or something like that. But even TextEdit sometimes has an issue. Different word processors have different benefits or detriments for using R. Some people have even ended up using Microsoft Word, something I don't recommend, but some people have done that. All of the R editors get rid of all of the extra formatting commands. Okay, but I pasted it into RStudio. Now, RStudio is sort of nice. It allows you to run the pieces that you want. In this case, we're going to want to run the whole thing just to see what happens. Okay? So what I'm going to do is I'm going to the bottom, and I'm going to just simply highlight the whole thing. Okay? And I'm going to click Run. Everyone see me clicking Run? Now the output comes here, and the graphics come down there. Everybody do that? Did it work? And you zoom through the graphics you have to highlight this window. You get different graphics here. You see this Windows command here? It's in the middle of the code. Windows and then 2 parentheses. That's used only for the Windows machines and only for raw R. It's not needed for RStudio, and it's not needed for the Macs. In fact, the Mac people have to get rid of it. Let me explain what's going on. There is a device, and the device means, give me another plot. I want another window open, and I want another plot. I want to see the plot. With the Windows machines, if you have one plot after the next, it will write the next plot on top of the first one, and you lose the first one. So it's like gone. And you have like 10 plots, and you end up with only one. So for the Windows machines, after every plot, I have to say, Windows, 2 parentheses, say, open up another window so I can have another plot so you don't get rid of the first one. All right? So that's what that's all about. On all of my programs throughout the whole course, or anything dealing with graphics, you'll see these little things, because it's needed for raw Rs for Windows machines. Those people who have Macs, delete this line. The Macs are already remembering that if you made a plot, you want to see it, so don't get rid of it. So the Macs keep the plots, and just by holding the command button down and the arrows, you can cycle through them and you'll see them all. Windows machines, if you don't have that, you'll end up with only one plot, no matter how many you make. Okay? So that is actually useful. For RStudio, it's not useful. It doesn't need it because RStudio remembers all the plots anyway. You're actually creating your programs here. You're actually writing them here, where it says the source. Does everyone see that? And then you click here and you save it. And you save this, you call it a name, and it saves it in your R working directory. Okay, so you save your program. I never save the whole stuff, the workspace and the files and everything. I just save the actual program. So I'm not going to save it here, but you are going to do that. And it looks like I have two programs. I'm not going to save that one. Okay, so it looks like I had 2 programs open, so it had 2 windows here. This is, and let's say you were starting from scratch. This would be empty. And then you would be literally typing in from scratch your program here. And then you'd be highlighting the pieces that you run, or the whole you want to run, you want to test, see how it goes. You click Run. The output comes out here, plots are over there. But before you're gone for the day, you click that little thing there, or file save, you save your program. So you see, when you're in R, it's a different thing. When you're in R, you have just the console open. So the question is, when you start doing stuff, R has lots of stuff that it outputs. I'm not writing the code in the console. I'm not composing it in the console line by line. If I wanted to use R to compose the code, which I don't want to do, but I could, if I wanted to do that, I could go File, New Script, and it produces a little text editor. And I could start editing it here, and then I'd have to save it, file save, I'd have to save that code someplace. Okay? So what I do, and I'm not the majority. I mean, most people in R use some type of text editor, such as some type of R editor, such as TinR, or they use RStudio, or that's what they normally work in. What I like to do for this course is to use some raw, basic text editor, so that you get a whole semester of seeing R work in its raw format. And then what I do is, in that text editor, I save the actual R code, and that's all I save. I don't save the workspace. So when I get out of R, when it says, do you want to save the workspace? I always say no, clean it out, get rid of everything, gone. If you save the actual workspace, it remembers variables and other stuff. It actually remembers things that it had computed, and I don't want it to remember anything. I want it to be completely like a computer that was empty, rebooted, empty. Other people don't do that. Other people like to save the workspace and say, I'm going to pick this up after dinner and I want to know exactly where I left off. Does everyone get it? You're going to decide what you want to do. So I'm telling you what I like to do, but I'm not making choices for you. I'm going to say some of you may like to save your workspace, but some of you may want to just say get rid of everything. With R, the workspace includes what they call objects. Every variable and every matrix and every thing that you create in there is an object in R. And it remembers all that stuff. And so I just like to say, dead, kill it, over, and I start up from scratch. So what do I like to do? I save my programs. That's all I want to remember. And if I want to start it up again over dinner, hey, I just open up the program in the text editor or whatever I'm using, copy, paste it into R, and I'm ready to go. 10 seconds. It's your preference of what you want to do. You have to decide what your particular workflow is going to be like. So here I have R in its normal console. Again, you're never composing in here. You're never composing in here. You're actually just pasting your code in here. Your actual composition is going to go somewhere else. Now in this case, I have WordPad open. If you're on a Mac, you could try a text edit. Text edit will give you a little bit of problems because that does remember the formatting commands, because it's a Mac. Macs always remember formatting commands. Sometimes you can use other, but anyway, RStudio, you won't have that issue. RStudio is designed where if it sees any hidden formatting commands, it scratches them out. So you won't have any problems like that. Some people have used Microsoft Word, which I don't recommend, but they have successfully used it, and actually cut and paste into Microsoft Word, and then pasted it into R, and that has worked as well. Other people will say, no, don't do that because Microsoft Word changes spelling and does all types of other things with other commands. But I have seen Mac people do it quite successfully. So it's going to be your own way of doing it. All right, so see, I don't understand that I don't want you leaving this course in a semester thinking that RStudio is R. Does everyone understand? I want you to know that R is R, and RStudio is something that somebody wrote that has a nice frame around it, that has pretty windows. Does everyone understand? And you can use many different versions of editors like that. So I want you to see R in its raw format when I do it. And I want you to get used to the idea that you are making choices on what editor you want to use when you use R. Okay? So I will use R in its raw format. So here I have WordPad. and I've pasted the data set into this, into WordPad. And now I would fix it, change it, do whatever I want to it. And then when I'm done with this, I would save it as a text file. Okay? So, what we're going to be doing here is actually going through this code and explaining why it works. On my web page, there is a link for R tutorial videos. I want everyone to watch all 4 of them and to do exactly what's on the screen. That's what I was going to do with the John Fox script that he just deleted from his website. You'll see 4 windows, actually 4 videos will show up. And I want you to start with the arithmetic operations. It'll include logs and everything, and I will speak while it's happening. So I want you to play them while you're running R at the same time. There's videos, one is arithmetic, the next one is working with vectors, the next one is working with variables, and the next one is data frames. Okay? So I want you to actually go through all 4 of those and get an introduction to all 4 of those things. What we do starting on Tuesday is to go through line by line of the actual program that we just did. All right? And we will be done going through line by line, I think, of the program on Tuesday, and you will be getting results and bringing them back in on Thursday. Depending on how fast we do everything on Tuesday, you'll either be handing something in on Tuesday, or, I'm sorry, on Thursday, next Thursday, or you'll be writing it up over the weekend. It's a very short assignment, only a couple pages of text, so it's not like a big job. So if we do finish it, if we do finish the whole code going through it on Tuesday, then it will be due on Thursday. But we'll have to wait and see how that goes. All right? Raise your right hand. You're going to watch the 4 videos. Everybody, right? Promise, promise, promise? Okay. All right.
Mm-hmm.